Howdy, howdy. This is Mr. Potter. Pi Day is coming up really soon. We call it Pi Day because March 14th is a lot like 3.14, and so this is a really good way of saying March 14th. The European way of writing dates doesn't work because April doesn't have a 31st day, and there is no 14th month, so we stick with this. This is Pi Day coming up March 14th. And pi really is the Borg of math. You may remember there was a Star Trek The Next Generation episode where the Borg were introduced. The humans in Starfleet had figured out that they kind of knew everything that was going on, and Q said, really, you think so? And they throw this monster at them. And we do the same thing with our kids. Our kids are in elementary school and they can handle 3 plus 4, and maybe they're learning 2 times 5, and then all of a sudden we whip out pi on them, this number that's not like any number that they've ever dealt with before. Sometimes this pi is even the first decimal that they even see before. And it's really their first exposure to what will become middle school and high school mathematics, and it occurs, sometimes even at the kindergarten level. A number of this magnitude really isn't even seen until we start talking about I when we get in our Algebra 2 class. But that's a story for another time. Briefly, though, let's talk about the numbers that people deal with. When we first start talking about the natural numbers. The natural numbers are numbers like 3 and 5 and 11, because we can see these things in nature. I can see 3 trees, I can see 5 rocks, I can see 11 bears. And then we have the concept of the whole numbers, where basically we just add 0 to this, because you can't see 0 trees, you can see no trees. And so the concept of 0 is added, which gives us the whole numbers. But then we add on top of that the integers. And we use Z for integers because the German Zahlen. Zahlen means number in German. And so this is where we get -3 or -1 or -12. Our negative numbers get added into this. But again, all of these still are numbers without decimals in them. Basically, they stop at the decimal point. Then we introduce this idea of rational numbers, and we use the letter Q for rational numbers to represent that. So this is our 3/4 and 0.296, the numbers that we can write as a ratio of 2 numbers. And these are the ones that either terminate or repeat. So for example, if you've ever seen 1/3, which is 0.3 repeating, that's one of these numbers that goes on forever. And then we start getting out to this larger group out here. And I'm actually going to divide this group up into 2 parts. One part are the algebraic numbers. So numbers like the square root of 2, or phi, which is 1 plus the square root of 5/2, the golden mean number. These are numbers that show up, and they can actually be solutions of algebraic expressions, algebraic equations. However, these are numbers that don't terminate and don't repeat. So when I look at square root of 2, I'm looking at 1.4142 ... And this is a number that keeps on going, but it doesn't repeat and it doesn't stop. On the other side over here, we have numbers called transcendental numbers. And this is where numbers like pi live. Pi, which is 3.14159265535 ... This continues on forever. It doesn't terminate, it doesn't repeat, but it's also not the solution to an algebraic equation. There's no algebraic equation where I can say x squared plus 4 equals 7, and I can solve this for pi. Pi deals in this nature of transcendental numbers, numbers that transcend equations. And this is part of the grand taxonomy of numbers. Now, keep in mind that we have lots of different approximations for pi. Probably one of the more famous ones we have is 22/7. Now keep in mind, these are all approximations. These are not true equalities. So this thing that you have on the clock where you have pi is exactly equal to 3.14, that's a bad thing. But we've got pi approximately equal to 22/7, and a lot of middle schools will use this approximation because they can deal with problems that have a 7 or a multiple of 7 for the radius or for the diameter. Now keep in mind that this only comes out to be 3.142857. It's a good approximation of pi, but of course it's deficient in this number right here. My personal favorite is 355/113, because what's really nice about this is that it's actually accurate to 6 decimal places, and I'm only using 6 digits. If I wanted to get something that was an even better approximation, I'd actually have to use much larger numbers, like 33,102 over 103,993. This is what I would need to do to get it just one more decimal place of accuracy. We use approximations all the time because pi has to keep going on forever, and our calculations don't always have to. If I use this value and try and get from the Earth to the moon, I'm going to be about 2 feet off when I actually hit the moon. So the question is, how much accuracy do we really need? Well, the 8 to 10 digits that your calculator will give you should be plenty enough. Now, that's not to say that there's not good reasons to figure out what more digits are. So we're going to briefly talk about the story of William Shanks. And William Shanks was an amateur mathematician in England, and he calculated pi to 707 digits. This is in 1873. And this was actually the most digits anyone had ever calculated pi to. And he used this idea that I can have a formula to find the arctangent of a particular angle or a particular ratio is going to end up being x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus. And this pattern repeats, the idea that the exponent and the denominator are going to match the whole way. So if I want to get something that's more accurate, all I have to do is take more steps, especially the fact that the tangent of pi over 4 is equal to 1, which means if I do the arctangent of 1, that's really just going to be 1 minus 1/3 plus 1/5 minus 1/7 plus ... But that's going to give me pi over 4. So if I just want to figure out what pi is, I can actually say that it's equal to 4 times whatever I got in this calculation. And if I want a more accurate answer, I just have to take more steps. Now this is what Shanks did. He owned a private school, and as a result of that, he had a lot of free times in the morning. In the mornings, he would do the calculations, and in the afternoon, he would check his work. Unfortunately, he wasn't that good at checking his work because only the first 527 digits of his calculation were correct. However, they weren't discovered until 1946. With the advent of computers. Nowadays, when we deal with computers, we're actually up to about 22 trillion digits of pi. Trillion. So in other words, 22, 000, 000, 000, 000, 000. That's how many digits of pi we know right now. This is as of October of 2016. And of course, that number has nowhere to go but up. And by the way, all of these 22 trillion digits, it took about 28 hours to verify those digits. So, great. Well, there have been some bad instances of pi as well. For example, the state of Indiana passed a law in 1887, what's called House Bill 246, where they basically set pi exactly equal to 3.2, among other things. There was this mathematician whose name was Edward Goodwin. And what he wanted to do is he wanted to give a gift to the state of Indiana, allowing them to use his pure mathematics for the state of Indiana to use at no expense, and other states would have to pay royalties to get that usage out of him. And this is one of the designs that he used over here, this circle over here. Notice that if this is a right triangle, and this is 5, and this is 5, he's basically saying that 5 squared plus 5 squared equals 7 squared by the Pythagorean theorem, or that 50 equals 49. Not really good math. However, keep in mind this House Bill 246 only passed twice, and it was on the third reading that a different mathematician came by, a mathematician from Purdue, and informed the legislators of their pending issue. So keep in mind that although the state of Indiana almost called pi something different, it actually occurs twice in the Bible. The first time that we have pi being set exactly equal to 3 is in the book 2 Chronicles, chapter 4, verse 2. Basically, he says he made the sea of cast metal circular in shape, measuring 10 cubits from rim to rim, and 5 cubits high. It took a line of 30 cubits to measure around it. So he's saying that the diameter is 10, and the circumference is 30. And of course, since pi is supposed to be the circumference over the diameter, he's basically saying it's 30 over 10, or 3. Now, keep in mind, it's not just once, but twice, because in 1 Kings, chapter 7, verse 23, this exact same calculation is made. So keep in mind that pi, according to the Bible, is 3. Of course, I think they made this change to pi in the Bible because if you take the first 144 digits of pi, they add up to 666, the number of the beast. The last thing I really want to talk about is this idea of why we call this pi. Because in Greek, the letter I is actually pronounced E. So, for example, when you have the Greek letter phi, they actually pronounce it phi. And when you have the Greek letter psi, they actually pronounce it z. And of course, if you take the Greek letter pi, they actually pronounce it p. So that's just something that we have to be aware of, is that we pronounce it in English different than most of the rest of the world pronounce it. And that actually has to do with our great vowel shift. The idea is that from the 1400s to the 1700s, English changed the way that it pronounces vowels. So most European languages which pronounce that letter as the E sound, we pronounce that as the I in psi or pi. Of course, the Greek alphabet is full of wonderful little pronunciations. Keep in mind when you talk about omega or omicron, when you talk about omega, you're talking about big O. And when you talk about omicron, you're talking about small o. So Greek is full of these little descriptors that have to do with their alphabet. Anyway, Pi Day is coming up. Happy Pi Day, everyone. Keep in mind that this really should be an approximation. It's not truly equals, but really it's just about having fun with our first real exposure to mathematics that we experienced as kids. Once again, this is Mr. Potter. Thank you for watching. Have a great day.